So I'm delighted to introduce our final speaker for this afternoon, which is Professor Chris Lintott from Oxford University and recipient of the RES-A Group Achievement Award this year. And Chris is going to be telling us about wonders of the Galaxy Zoo, morphological studies with a crowd.
Thank you very much. Hopefully this will work in a second. Thank you very much. I'm here on behalf of the entire Galaxy Zoo team, who have done all of the hard work and put in most of the effort. I want to thank particularly project scientist Karen Masters and our deputy project scientist Brooke Simmons, now at Lancaster, who have given countless hours to the effort of organising a collaboration. When we accepted the prize at the conference dinner at the National Astronomy meeting, a senior astronomer said to me that they were surprised to see an award going to galaxy morphology because that was old hat textbook stuff. After all, I think they meant it nicely. After all, we all know about galaxy morphology, and one of the reasons I love observational astronomy is that we make simple observations. We measure a mass, a colour, a brightness, and occasionally the shape of the objects that we're interested in. Hey, excellent, thank you. Right, old hat textbook stuff. Right, we look at objects, we make simple measurements, including shape. And in fact, of course, you know the image that would be in the textbook. It's this. This is the Hubble tuning fork, the Hubble sequence, the famous morphology. You have elliptical galaxies going from sort of round spheroidals to lenticular. And then you have these two branches of spiral galaxies, barred and not barred. And they go from SAS, BSC, as the bulge becomes less prominent and the spiral arms become looser wound. Textbook, but wrong, at least that little bit. It turns out that there's no connection between the bulge size of a galaxy and the spiral arm wounding. Here's a recent result from a paper led by Karen. This is the galaxies from essentially the Sloan Digital Size Survey. That's a winding parameter on the y-axis, tightly wound galaxies at the top, and that's bulge size on the x-axis. So galaxies with small bulges can have any arm winding you like. So these two factors, which are correlated and mentioned in all the textbooks, don't actually go together. And we know this now because we were able to do morphology on a grand scale, which we did, as most of you know, through Galaxy Zoo, a project that asked citizen scientists, volunteers, to classify large amounts of data for us. And it was in this room in 2007 where I sat at the back during an RAS ordinary meeting the day that we launched this project and realised that something very odd was going on. I'm afraid I wasn't paying any attention to the talks. I was trying to work out why our newly launched website wasn't working. And it wasn't working because this is what was happening. This was the number of classifications per hour provided by Galaxy Zoo volunteers in the first 2 days of the project. That gap at around, say, 3 to 10 hours is the point where the entire Sloan Digital Sky Survey server went offline because of the traffic that was heading that way from the hundreds of thousands of people trying to classify galaxies. Because this idea that you can help science using a few minutes of your spare time really caught on. We were quickly getting tens of thousands of classifications per hour. We had lots of people look at each galaxy, and we were able to produce statistically significant results. There's a whole part of the story in that Galaxy Zoo has inspired Zooniverse, a platform for similar projects, including, incidentally, one where a volunteer has found exocomet signatures in Kepler data, which is quite satisfying, and even a spin-out company in Oxford called 1715 Labs. But what I thought I'd do today is, rather than take you through the history, I thought I'd show you a few of my favourite results from the 12 years that we've been running Galaxy Zoo. And the first one was a confounding situation. We asked Galaxy Zoo volunteers in the original version of Galaxy Zoo to tell us which direction the spiral arms of a galaxy were turning. So we've got S-shape and Z-shape galaxies, clockwise and anti-clockwise spirals. And we did this because there was a paper in the literature that claimed a cosmological excess of anti-clockwise spirals, which is a result that makes no sense whatsoever. It breaks the Copernican principle. You end up sort of postulating invisible magnetic fields in the universe and some cosmic conspiracy to do this. But that result was based only on 2,000 galaxies. We had 250,000 spirals, and we found an excess of anti-clockwise spirals as well. We attempted to publish that and wind the cosmologists up, but instead we just reversed the images that we were showing to people. And so now we expected excess of clockwise galaxies. But actually, we still got more anti-clockwise classifications. It's easier to see spiral arms when they're anti-clockwise than clockwise. And one theory as to why this is called the rotating figure hypothesis. So I want you to imagine you're looking down on this cat. Please put your hand up if you see the cat rotating clockwise. Okay, what about anti-clockwise? So first of all, it's strange that we don't agree, right? Secondly, how many people have seen it change? If you want to see it change, if you do this, it makes no difference at all, but it amuses me, so that's good. What's happening here is that your brain is interpreting a two-dimensional object in a three-dimensional world. And there are a couple of choices you can make, and if you watch for long enough, your brain will flip between them. Something similar, we think, is going on with the galaxy images. Luckily, we were able to... I love this slide. I can say anything when this slide is up, because none of you are listening to a word I'm saying. I'll come back in 20 minutes. I'll put it up again at the end. What's nice is once you've measured this effect, we could adjust for it and use the spin for science. We found, for example, that the odds of two galaxies spinning in the same direction, two spiral galaxies, go up dramatically when they're next to each other. So galaxies that are close together tend to spin in the same direction. And what that means is that they probably inherit their spins from the larger cosmological structure. The old idea where you have two galaxies spinning each other up via a tidal torque, where you'd get one turning in the opposite direction to the other, is probably wrong. And we could look at how the other galaxy properties depended on that. So those are studies involving the whole bulk of the data set. In the case of the original Galaxy Zoo, about 900,000 well-classified galaxies. We can also look at subsets. Here is a plot from a paper by Brooke Simmons. This is the bar fraction of spiral galaxies over cosmological time. So we also classified not just Sloan, but deep Hubble surveys of galaxies in a consistent way. And you can see that there was an epoch in the past where barred spirals, like the one on the right here, were rare and only occasionally turned up. And bars have been a big feature of the Galaxy Zoo team's work and indeed leisure over the course of the project. I'm particularly fond of a result from my ex-student Shandor Crook, who's now an ESA fellow at ESTEC, who found a population of dwarf galaxies in Sloan where they have bars, but the bars are not at the centre of the galaxy. These are offset bars. And there's some theory behind this which suggests that these are the result of near-miss interactions. So you have your little dwarf galaxy sitting there, another galaxy flies past, and the material in the dwarf sloshes around in the gravitational potential. The bar stays fixed, but the material sloshes around in the potential. The trouble is we can't see any evidence for that interaction, and so these offset barred galaxies, of which we have a few thousand, are a bit of a mystery. That result, I think, is pretty typical of a pattern that keeps happening to us, and I think is typical of astronomical big data in general. We're fond of talking about ourselves as a science that these days confronts big data. I had a meeting today with some ex-astronomers at Google who got their jobs there partly because they come from a field that's good at dealing with big data. But actually, the fun bit is taking 1 million galaxies and finding the few thousand or a few hundred that share a property that you want to study. And so what we're good at is filtering big data to find interesting subsets. Another example of that in Galaxy Zoo was inspired by this object. This is NGC 4395, a nearby flocculent spiral. I like saying the word flocculent, so I just worked it into the talk again. Flocculent spirals are highly star-forming, but this one's interesting because it's a spiral galaxy, it's a disk galaxy with no bulge. If you use Patrick Moore's old analogy of a spiral galaxy as being two fried eggs clapped back to back, this galaxy has no yolk to it. And what that means is that this galaxy is guaranteed merger-free. If you have even a minor merger in your history as a purely disk galaxy, stars are kicked up out of the disk, they go into orbit, and they form a bulge. So you can guarantee that this galaxy hasn't had a major merger since it became a disk. And so we can use galaxies like this as a laboratory to study the effect of mergers on the galaxy population. This is our control sample that have evolved in a purely secular way, a non-merger way. And this galaxy has been studied by other people, and it was noted because it has a particularly small, or rather a particularly light, black hole at its centre. The mass of it, it's not a supermassive black hole, it's just a massive black hole. It's about a factor of 10 smaller than you'd expect from the galaxy, and that's nice, because that suggests that mergers build up black hole mass in galaxies. Well, we could test that. Brooke, again, along with Becky Smethurst, then a PhD student with me, now a research fellow at Christchurch in Oxford, grabbed this sample of 101 bulgeless galaxies from Galaxy Zoo. The point sources you see in the centre there are not bulges. Those are luminous AGN. So these are bulgeless galaxies that are currently growing their black holes. And we decided to study how their black holes compared to normal galaxies which had had mergers. So here's the plot. In red are normal galaxies. This is what in Oxford tends to be known as the Megorian relation, but the black hole mass to bulge mass relation for normal galaxies. Here are our galaxies. Actually, what we did to put them on this plot is take a conservative limit for the bulge mass. So for each galaxy, we're saying if there is a bulge there that we can't quite see, how much mass could be assigned to that component. So these are conservative limits. This is the best fit to that data, given the population. This is the line the referee made us draw, because they didn't understand statistics. But in either case, whether you believe us or the referee, the grey lines are different from the red line. And I promise you, this is the most boring result presented at the Royal Astronomical Society today. We picked a bunch of galaxies which are bulgeless. And I've shown you that for given black hole mass, they have less bulge than we expected. However, half the slide is empty, which is good because I can bring up this plot, which is not the bulge mass, but the total mass of the galaxy. And these galaxies lie on the normal black hole mass, total mass relation. So in other words, galaxies grow their black holes to the size we'd expect without the benefit of mergers. So mergers are not important in the growth of supermassive black holes in the centre of galaxies. It's an excellent and interesting and counterintuitive observational result. So, of course, the theorists told us that we should have expected that all along. In this case, this is Gareth Martin's work. He's just finished a PhD at Hertfordshire. This is from the Horizon AGN simulation. This is the cumulative growth over time of black hole mass. So top left is black holes now. And then you can see the red line here is the total contribution to mergers. So in the simulations, a third of the growth of black holes is merger-driven. The rest of it is not. And we've gone on and we've got a Hubble program looking at these galaxies in detail, and we're using them as a test case, as a laboratory for understanding secular growth in galaxies. One of the recent results from that program, again from Brooke and Becky's work, is really interesting. We found that I've got it written down, so let me show you. There we go. So we've discovered two interesting facts. We've measured the inflow of material, or inferred the inflow of material onto these growing black holes for both normal systems and merger-free systems. And we've also measured the outflow rate, how much is expelled from the region just around the supermassive black hole. And we've got two slightly counterintuitive facts. The first one is that the inflow rate to these AGN is much higher in merger-free systems. So even though they haven't had a merger, large amounts of material are being delivered to the centre of these galaxies by transport along bars, through spiral arms, through instabilities in the disk. Fact two is that the outflow rate in jets from the supermassive black hole or from inside the region is higher in the systems that have had mergers. So we're putting more material into our secular merger-free galaxies, but more of it's going on to the black hole. The efficiency of growth is higher. We don't really understand this result, and it depends on a small number of galaxies, but we think that what's going on is some difference to do with the black hole spins. I don't really have time to go into this, but we think, if you imagine, just take the top part of each diagram here. On the right here, you've got growth of a black hole via a merger. You have material coming in from all directions. Each successive episode of merger-driven growth is from a different direction. It depends on the merger of the galaxy, the geometry of the large-scale interaction. On the secular side, you have a nice stable disk. Material always flows along the disk. And so the spins of the black holes are different, and perhaps their behavior is different. So I've now gone from, we started studying 1 million galaxies, then we were studying a couple of 100,000, then we did a couple of 1,000 offset bars. This work was based on 100. Let's go all the way down to studying one special object, because one of the things that Galaxy Zoo taught us was that studying individual objects can still be interesting. We realised that early on when Hanny van Arkel, who's pictured here, she's a Dutch school teacher, so an early participant in the Galaxy Zoo project, spotted this faint green blob, which you can see on the right-hand side here. She called this her voorwerp, which, apologies to Dutch speakers in the audience, I still don't have the pronunciation down, we thought was a technical term. You can Google Hanny's voorwerp, you'll find it in the technical literature. Voorwerp means thingy in Dutch. And what was interesting about this process was that Hanny did that most obvious of scientific things. I found a weird thing, what is it? I haven't seen anything like this before, what is it? It's really basic, interesting science. But more than that, she became an advocate for this object. We sort of didn't care. We were busy worrying about spiral arms and correlations with bulge masses and so on. But Hanny wanted to know what this thing was, and so her and her friends on the discussion forum that came with the project made a case that we should find out what this thing was. We thought it was a nearby planetary nebula, but it turned out to be at the same distance as this neighbouring galaxy, IC 2497. So this is a large-scale object. It's a galaxy-sized gas cloud, and the spectra that we obtained from the WHT, if I remember correctly, told us that the voorwerp is made of hot gas at a temperature of about 50,000 Kelvin, but that there are no stars. There's no stellar continuum there, so there are no hot stars to ionize that gas. And so we quickly arrived on a hypothesis that this was essentially illuminated by activity at the center of the neighboring galaxy. If you have jets from AGN with spiral galaxies, they're normally perpendicular to the disk. This is perfectly positioned for this to be the case here. The only problem is that there's no AGN at the center of IC 2497. We looked with XMM Newton and found no evidence for that at all. And so we had this puzzle, and then we realized that we were playing with different timescales. This was work led by myself, but particularly by Bill Keel at the University of Alabama. Bill pointed out that the voorwerp tells us about the state of the galaxy 50,000 years ago, because there's a light travel time to get from the center of the galaxy to the voorwerp. So we're seeing the ionization state of the galaxy as it was 50,000 years before what we now observe. And in fact, when you work that out, this galaxy 50,000 years ago will have been the brightest quasar in the sky. Its nucleus would have been just under magnitude 8. You would have been able to see it with binoculars. And it has faded rapidly over the course of the last few years. What's really exciting is that Hanny became quite famous, at least in the Galaxy Zoo world. We flew her to a meeting at the AAS so she could present her object. And other volunteers wanted that kind of attention and fame and discovery as well. And so we quickly had a whole collection of what I think in Dutch would be voorwerpen, but which tended to be known as the voorwerpjes, which is the diminutive, because most of them were smaller. So here they are. This is a collection of ionized gas clouds mostly around AGN, or galaxies which once had AGN. You can see these are mostly disturbed systems. That makes sense if you're going to have gas out there to ionize. And about a third of them show evidence of rapid fading. And so we now have a cottage industry measuring the fading of AGN on timescales that were previously inaccessible to us, on timescales of tens of thousands of years. So it's been great fun. I didn't want to try and give you any sort of systematic overview, but I want to give you the sense that the richness of the data generated by our generous and enthusiastic citizen scientists is immense. And it's been a lot of fun working our way through that. I want to finish with a word to the future. We're very much focused on future surveys. Lots of the team are involved with LSST, which is now beginning to look like a real observatory. We're involved in Euclid, which will provide images of millions of galaxies a large proportion of which may be interesting morphologically. And we've realized that for data sets of the size produced by Euclid in particular, but LSST as well, we need to be smarter about what we ask our volunteers to do. So my student Mike Walmsley is an expert on machine learning, and he's built a Bayesian neural network. So this is a network that classifies an image of a galaxy, but it classifies it with uncertainty. So we get a probability distribution for a galaxy property. And then what we do is we take the galaxies for which the machine is, and then you clone the machine 20 times. Each clone is slightly different. It's not a perfect cloning process deliberately. And then you look for the galaxies where each individual instance of the machine is certain, but where they disagree with each other. And then those are the galaxies that you show to the volunteers. So if you go to Galaxy Zoo today, you will see there's a button that says Enhanced, and that will show you those galaxies which our machine thinks it most needs human help to see. And we have this virtuous cycle of a human-machine classifier running live in real time. Finally, I want to point out that I've deliberately made this a science talk. I wanted to make sure that you realise that morphology was not just textbook science, and I wanted you to realise the immense depth and excitement of what we've been doing. But I do want to talk a little bit about the volunteers. We've had hundreds of thousands of people take part in Galaxy Zoo. Most of them, before they hit the site, had not really considered astronomy, certainly didn't consider astronomy part of their lives. And yet these people were excited because they had the ability to contribute to science. In science, we have a really strong case of what in the museum world is called threshold fear. Threshold fear is the idea that you won't go up the steps of the National Gallery through this rather imposing entrance and into the gallery unless you already think that you can get something out of looking at a painting. No matter what the gallery does inside to make that experience more accessible, more interesting, more varied, more diverse, you're not going to go up the steps unless you think it's for you. Galaxy Zoo and projects like it provide a way of people stumbling into doing research in science and getting over their threshold fear that's induced by the way our culture talks about and thinks about science as a profession for the few and not for the many. So with that, I'll say thank you very much. I'm happy to take any questions.
Wonderful. Thank you very much, Chris. Questions, please, from the audience.
Thanks, Chris. That's made me really think. I've come up with two questions. They're both related to the spirals and seeing things both way around. Have you taken the spirals one way, spirals the other way, and put it into some machine learning detection system? Obviously, it won't be fooled, but has that experiment been done?
It would be fooled because it would depend on the training data. So you need
yes.
so a machine can so the machines as people in fields like face recognition are discovering, machines inherit our human foibles when we train them on our data.
Yes.
And so they would be fooled. The thing we haven't done is that it's been suggested that it's to do with the fact we read from left to right. And so I need to go back and run this project in a language like Japanese or Hebrew, which reads right to left, and see if we get the opposite result. So that's the next experiment.
Right, okay, I think that actually impinges on my second question, which was, do we know why humans do...
No, it's linked to the fact that your brain is interpreting... Our brains are not set for 2D images. Right, they're expecting three-dimensional objects, and there are choices that your brain makes, and there are biases in those choices. So if I show the cat rotating to a large audience for a long time, we tend to pick anti-clockwise slightly more than clockwise. But I don't think it's known why that's true.
Right, I just wondered if left-handed or right-handed people...
The rotating figure illusion doesn't have a left-handed, right-handed thing, but we haven't tried it with galaxies. We did end up at some point with people classifying galaxies in brain scanners, but that's a whole other story.
Right, yes. Thank you.
By the way, Japanese doesn't read the right.
Oh, does it not? Oh, sorry, thank you. It's probably good to know.
Yeah, thank you. You're trying to get real truth, really, with these galaxy morphologies, but actually you're looking on the images on the screen, certainly you're looking in 2 dimensions. Therefore, the orientation of that galaxy to us must have some bias in it or some part in it. So how do you deconstruct that?
with difficulty. So you're absolutely right that inclination's a problem. A lot of the time we can make simplifying assumptions about the shapes of the galaxy. So for example, if you assume that the disk is circular rather than elliptical, then you make a guess at the inclination. Really, though, you're hoping that those effects, you think carefully about those effects and hope that they even out in a large population, because after all, the inclination should be, on large scales, random. The other thing we're doing, of course, is that we're looking at a projection of the stars, not at the way anything's moving in the galaxy. And one of the most interesting things that's happening at the minute is the connection of the kind of work I've been talking about with surveys like MANGA, which are using IFUs to look at the kinematic classification. And so our hope is that we can use these large-scale samples classified with visual morphology and then use MANGA and other IFUs to explain what we're seeing by looking at a smaller number of galaxies in detail. But you're right, the universe continues to be annoyingly distant and two-dimensional as viewed from Earth.
Hi, I wonder whether we do have a real asymmetry or whatever it is. After all, the Planck data shows that cold spot, and there's only one, and there's an asymmetry in the cosmic dipole. So perhaps we're in a left-handed universe.
Yeah, so that was the claim made by Michael Longo, who's the guy who published the initial claim. I can tell you we see no evidence for because we can, when we show people mirror images, we can measure that bias and then account for that. And once we've done that, we see no evidence for an excess. Longo still thinks he's now corrected his method, and he still claims that there is indeed an alignment with some of the cosmological features, but such a result would be brilliantly fun because it would bring down several pillars of modern cosmology, and I don't think we've got the evidence for that yet.